I'm going to tell you about photonic time crystals in Bose-Einstein condensates. And this work was done together with Kartik Eswaran, who is in the audience. And I also recommend his poster on time quasi-crystals today. Let me start with photonic crystals in space, more traditional crystals, just to begin. So if we have an optical medium fabricated so that the refractive index changes periodically in space, then propagation of electromagnetic waves possess solid state-like properties. And especially we can see band structure in the frequency or energy domain, meaning that there are gaps, and that gaps correspond to the frequencies for which electromagnetic waves cannot propagate in the medium. Photonic crystals in space, but now photonic time crystals. In photonic time crystals, now we assume that we have spatially homogeneous system, medium, but the refractive index is, or permittivity is changing periodically in time. And then, for example, electric displacement field can be characterized by the well-defined momentum because we have homogeneity in space, but there is some non-trivial time dependence, and this time dependence we can obtain by solving basically Maxwell equations. And the Maxwell equation for the displacement field can be reduced to this form, and please remember this form because this equation will appear again in a moment. And due to the fact that we have the permittivity changes periodically in time, we can look for the Floquet solutions, which are characterized by the quasi-frequency. Omega is quasi-frequency. And if we do so, then we obtain band structure, but in the momentum domain. So there are certain gaps in the momenta, and it seems that for this momenta, electromagnetic waves cannot propagate in the medium. But actually, it is not true, because in the gaps, the quasi-frequency are purely imaginary. And the solution in the gaps corresponds to the exponentially diverging in time electromagnetic waves or exponentially decaying in time. But these are eligible solutions because we have optical medium which oscillates in time, and this medium can generate electromagnetic waves which increases exponentially in time. And I would like to also stress that this kind of behavior has not been observed so far in the optical frequency range. And this is basically because the permittivity has to be changed substantially and with the frequency comparable to the optical frequency. So that's photonic time crystals. But now, Bose-Einstein condensates. And let us consider homogeneous Bose-Einstein condensates. And this can be condensate wave function can be described by the Gross-Pitaevsky equation. But now we assume that the scattering length is changing periodically in time. And this equation still possesses homogeneous solution, the solution which describes the uniform distribution, constant distribution of atoms in space. And now we are interested in the excitation of this Bose-Einstein condensate. And because the condensate is homogeneous, then again, excitations can be described and can be characterized with the well-defined momenta. And of course, if we assume that the excitation is weak, then we can use Bogolyubov approach. But let us rewrite Bogolyubov equation in a slightly different way. But first, let us define artificial displacement and magnetic fields, which are defined this way. And if we do so, and from the Bogolyubov equation we eliminate this artificial magnetic field, then we end up exactly with the same equation which I showed you before. But now the scattering length plays the role of the inverse of the permittivity. So we have the same equation, so we should expect the same solutions. And this is an example for typical experimental parameters, rubidium atoms, and scattering length is changing in this range, and with frequency of 800 Hertz. And this is a solution of the Bogoliubov equation. So indeed, we see the formation of gaps in the and band structure in the momentum domain, and the modes corresponding to the gaps are unstable modes of the Bose-Einstein condensates. And this band structure can be easily observed in the experiment, because the experiment can look as follows. We start with the Bose-Einstein condensate. We prepare Bose-Einstein condensate for the constant scattering length that can be modeled by the ground state in the Bogoliubov approach by the Bogoliubov vacuum state. And then we turn on modulation of the scattering length. And after, for example, 30 modulation periods, one can measure momentum distribution after, for example, time of light. And then what we see these pronounced rings. And these pronounced rings are related to the excitation. Okay, initially we have Bose-Einstein condensate in the ground state. There are different, let's say, there is non-zero quantum depletion, and the depletion corresponding to these unstable modes is growing exponentially in time. And these rings actually precisely matches, the band structure in our let's say, quasi-frequency spectrum. Yes?
Sorry, I have a very stupid question. I missed something. What sets the relevant momentum scale here? So it may not, I think, in your case, or where do these gaps appear?
What?
What momentum do these gaps appear?
Okay, this is related to the unit is related to basically to the sound velocity. So this is let's say, more or less this time scale. Okay. Yeah, let's say the momentum scale. And so we are here. So that means that the photonic time crystal behavior can be realized and observed in a Bose-Einstein condensate. But now let us consider topological properties. And topological properties of photonic time crystals were analyzed by Moti-Segiev group. So suppose that we have a periodic change, that scattering length changes periodically in time, but we assume that this function is time reversal symmetric. But if we shift this modulation by half the period, so just to show you, then of course for this driving we obtain obviously the same band structure. But when we calculate the Zach phase of the bands, then for these two different way we drive the system, the Zach phase characterizing the bands are different. So what it means that what we can do, we can, let's say, drive the system in a certain way. We have photonic time crystal, and then we change the way we drive the system. So we have another photonic time crystal, but these both have different topological properties. And of course, we should expect temporal edge states, and that was demonstrated by Moti-Segiev group. But now let us look a bit more closely to the modes coming from the gap of this let's say quasi-frequency band structure. It turns out that there is one unique mode, unique momentum, and when we take this mode and we take the diverging mode in one of the time crystals, then of course this diverging mode diverges in time. But when we switch to the other photonic time crystal, then this mode matches perfectly the decaying mode in this second photonic time crystal. So it starts decaying exponentially in time. And this is exactly the edge state expected from the topological analysis. But there are also other modes from the gap which are eligible. And there is another mode. If we take again diverging mode, then this mode diverges. And when we switch to the second photonic time crystals, this mode again matches the decaying mode, but not exactly. There is some contribution from the diverging mode. So what it happens, that initially we see, let's say, decay of the amplitude of this mode, but at some point, this small contribution from the diverging mode takes over, and then we see increase. And then, looking at this behavior, we can propose stabilization procedure, because if we, at this moment, switch back again to the previous photonic time crystals, we do not allow the diverging mode to grow. And if we keep doing repeatedly, then we should strongly stabilize Bose-Einstein condensate against depletion. And indeed, this is an example. So the red curves is related to the standard driving of the system. We have a well-defined, let's say, frequency one way. But the blue one is related to the let's say, driving when we repeatedly switch from one to the other photonic time crystal, then that stabilizes the system. In photonic time crystals, one of the important problem is emission of radiation by an atom embedded into the photonic time crystals. And actually this kind of phenomena can be investigated also in a Bose-Einstein condensate. So what we need a focused laser beam with intensity which is modulated in time. And then we obtain the additional potential for atoms, which is changing let's say oscillate periodically. And if the potential is weak, then in the Bogolyubov description, the presence of this potential results in the inhomogeneous term in our Maxwell equations. And that can be considered as a time derivative of the current density induced by an localized oscillating dipole. And one of the attractive options is to use Bose-Einstein condensate in optical lattice to emulate the photonic time crystal, because then we don't have to modulate S-wave scattering lengths. Instead, it is enough when we modulate tunneling amplitude. That, I guess, experimentally it is much easier because you can only modulate the intensity of the lasers that create optical lattice. And then we can obtain the band structure not in the momentum but in the quasi-momentum domain. And optical lattice is also attractive because we can switch to the strongly interacting limit, which is highly challenging in the photonic time crystal business in optical systems. And that's all. So summary and outlook. So photonic time crystals are optical media where temporal modulation of the refractive index creates band structure in the momentum domain. But experimental realization in the optical frequency range remains challenging. But it turns out that homogeneous Bose-Einstein condensate with temporal modulation of the scattering lengths can reproduce the physics of photonic time crystals, and experimental realization seems straightforward. And it turns out that the Bose-Einstein condensates offer a playground for the investigation of a broad range of photonic phenomena. I told you about temporal edge states. I didn't have time actually I had the time to tell you about temporal Anderson localization. This is the work we done also with Kartik and Ali Kupai, because it turns out that when you have a medium which permittivity fluctuates in time, there exist solutions corresponding to the exponential emergence of the electromagnetic waves and then exponential decaying. Time reflection and time refraction can be investigated. Suppose that we have excitation propagating with the sound velocity, and then we abruptly change the scattering length. Then, of course, this excitation starts propagating with a different velocity, but there is also, let's say, reflection into the opposite direction. There appears. So we both observe refraction and reflection. And I told you that emission of radiation by atoms embedded into photonic time crystal can be investigated. Nonlinear processes in photonic time crystals, which are in Bose-Einstein condensates, which are with a high level of control, can be realized. And also, more importantly, strongly correlated regimes, which in optical media are really highly non-trivial. And I encourage you to join time crystal fields. So that is why there is a list of review articles and books. So just that's. Thank you.
Thank you very much. I have one obvious question. It's the question of heating in your system. Did you consider it? When you have those modes blowing up exponentially, probably you have it, right?
Yeah, but that's actually takes into account, this is just a mechanism of dynamical instability. And this dynamical instability is the effect which we want to detect, because that allows us to detect gaps in the momentum domain. So that's, but okay, no thermal effect we consider, so that's true.
Oh, no. Yes. It's not a question. May I ask another one quickly? I was kind of hoping to hear about the Anderson physics, and I was hoping to be able to ask about Aubry-André model in this system. Mm-hmm. Is it premature, or did you think about it?
But this is, it depends in what way we modulate the medium. If you modulate in a pseudo-random way, then you have exactly this phenomenon.
But it's a 1D model, right?
It is 1D because...
So I would prefer to look at the Aubry-André model rather than Anderson.
Yeah, but this is all 1D model because time is 1 degree of freedom. But the system is a three-dimensional. But you look only at the properties in time. So in this, say you can reduce to the one-dimensional André-Aubry model or Anderson model. Mm-hmm.
Okay. Yeah, I saw you had more questions. Yeah, please.
Mm-hmm.
So I was wondering. Thank you. I was wondering when you change, for example, in the system that you study, the interaction, or in the photonic system epsilon. In time, if you do it very quickly, there will be retardation effects in your system because the velocity of sound is constant, and in the photonic system because of the velocity of light is finite. So what would be the retardation effects that you can see in this system if you do it sufficiently fast?
Actually, what we consider if we change let's say, for example, if we change the scattering length in this way, it is so quick that during the changes phase, the system doesn't react. So that's...
So you always have retardation effects that you have to take into account, or not?
Actually, though, we in a sense, we don't... what do you mean? You mean that when you change something, we have to wait something to respond to the system, right?
Yeah, I mean, if you perturb your system very, very quickly, so because it takes time for information from one point to come to the other point about the value of the epsilon of your system. So like in condensed matter, these retardation effects have to be taken into account if you calculate, let's say, the conductivity or some other response function, if you do it very, very quickly. So I mean, obviously here it should be the same.
One thing what we assume that we can change the, let's say, scattering lengths uniformly in the same way. So this is one thing. So that's... and the problem of retardation is included here because you have a finite speed of sound, and that if you want to, it's just included in the description. In this, it comes out from the solution of the equation. If you obtain the, let's say, Floquet solutions, it is just let's say, a kind of stationary state. But when you want to let's say, to simulate the experiment. So this is just, we start with the ground state. you let's say integrate Bogolyubov equation of motion. That's it. And of course, finite sound velocity is included in this description.
Okay.
Maybe we can talk later because.
Plenty of questions.
Yeah, very nice result. I was wondering, could you go to the where you change the phase of the drive between the blue and the red? You mentioned here that if you change it suddenly, you get these edge modes. Could you change the phase continuously slowly to get a topological pump or something like that?
Yes, yes. It's just, you have, let's say, plenty of things to.
Yes,
so
great.
Yeah.
Which are the symmetries protecting these topological edge modes?
Sorry?
The symmetries protecting these topological edge modes?
You assume that there is, as I said at the beginning, you assume that you have a driving which is in time reversal symmetric, and you switch to another driving which is shifted by half the period. So both of them are time reversal symmetric, and then you can characterize both ways in a proper way by the Zag phase. So this is the symmetry.
So you're indicating here rectangular pulses, and I suppose it doesn't matter so much what kind of periodic pattern you use. I mean, probably you could do just the simplest usually is something sinusoidal, but then my question is there some difference that you would expect if you do this in this way, or in or take just the lowest Fourier component?
Okay, this, let's say, square wave modulations we have chosen because this is easy to, let's say, to solve the evolution equation, because you have to do it in intervals. But this is not at all essential. The one thing is that if you start with a simple harmonic driving, then you can create only one gap. The higher harmonics usually add more and more gaps. So that's, yeah.
Can you open the slide where you have two curves, red and blue, switching this?
Sure.
So you have two frequencies. One of them is for this fast frequency, red or blue, and another is switching frequency.
Yes.
So do this ratio between the high frequency and switching frequencies integer number, or it's any number?
It is. In our case, yes, it is, because in a sense that you have to, we switch at the, let's say, in the middle of the half the period, right?
Mm-hmm.
But concerning the different frequencies, of course, if you have this protocol when we repeatedly change the driving, then you can say that we have longer driving period, basically.
Yeah, so basically it's just become, again, periodic, but with longer period, if
yes.
the ratio is integer.
Yes.
Mm-hmm.
And then what we obtain basically different band structure. But it turns out that this big gaps with a large imaginary part of the quasi-frequency are strongly suppressed. So that is why we obtain this stabilization mechanism.
Yes.
Can also use this one, I guess. So, I mean, this reminds me of some work that Cheng Chin did, like experimentally 10 years ago. So, if you go away from rubidium, but you go, for instance, to cesium or potassium, where you have a Feshbach resonance, then you can modulate the scattering length directly by changing the magnetic field. And what Cheng did was similar to the setup here, a periodic modulation of the scattering length. And then what they saw were not these kind of coherent rings going out, but they saw that these rings fragmented in like a whole series of jets going out in separate directions, because there's like some kind of higher order instability then in the system. So I was wondering whether that also shows up on the Krauss-Bolierski equation.
Yes, but just what we wanted to demonstrate clearly, the photonic time crystal phenomena. So that means that what we assume that excitation, or for example, the excitation is weak. So basically, this is just a total depletion. So if you wait more, that what we, let's say, for this moment we plotted the momentum distribution. If you wait more, then you enter the nonlinear regime. That's for sure. And this is also, from the perspective of photonic time crystal, it is very attractive because you have a well-controlled nonlinear phenomena. And also one maybe more question, because this is one remark that we have, this is Maxwell equation, but that we assume that we are in the, let's say, linear part of the Bogoliubov spectrum. And then you have exactly linear, let's say, Maxwell equation for linear media. But you can go for, let's say, for higher momenta, then you have you emulate the dispersive, let's say, media. So this is also attractive from this.
Okay, thank you. I think time's up.
Thank you.
Thank you.